In the last section, we looked at constructing a confidence interval for the population mean mu when sigma was known. Now we're going to do it where sigma is not known. And instead of using the standard normal distribution, we are going to use what's called the student t distribution. The name student was used as a pseudonym for William Gossett, who created this distribution. You can see the formula for finding a t-score, and the difference, we've seen something very similar to this before. The difference is it has S for the sample standard deviation instead of sigma for the population standard deviation. Now this does increase the unreliability of the result, and so to compensate for this increased unreliability, we use t-scores instead of z-scores. The t-scores will come from table 5. The z-scores came from table 4. And so one of the things that you have to do in solving these problems is recognize when you're going to use a z-score and when you're going to use a t-score, because they involve different tables. Now, the table 5 for t-scores has another thing that's a little bit different from what we have looked at before. It's called degrees of freedom. Basically, the number of samples that can vary after certain restrictions have been imposed on all data values. The degrees of freedom, or df, equals n minus 1, where n is your sample size. The idea is that if we know that 10 scores have a mean of 80, and we know 9 of those scores, then we automatically will know what the 10th one is as well, because again, altogether they had to have that mean of 80. And so we might not know it right off the bat, but we can determine it because we know the other 9. There isn't going to be any choice in the matter of what that 10th one will be. It's dependent on the first 9 that we already know. So, in order to find our t-score, our TC, critical value, that's a t-score, we have to first determine the degrees of freedom. That'll tell us what row in the table to use. We will use table 5 to find the critical value using the degrees of freedom and the confidence level. We will use alpha equals 1 minus the confidence level and the area in 2 tails, or alpha over 2 and the area in 1 tail. Now before we go on, let's just take a quick look at this table. And one of the things to note is that in the same column, we have area in 1 tail and area in 2 tails, and of course it's just double because of the symmetry of the situation. Off to the side, we have the degrees of freedom. Now, if we go up to where the values get very large, note that they do not go by ones anymore, or even by tens. They go by hundreds or 500s or thousands. When that happens, if our sample size tends to fall between any 2 of them, we will pick the one that is closer. So, just as a quick show, if we said we had a sample size of 11, well then that would mean a degrees of freedom of 10. And then if we had a 95% confidence level, well then that would mean an alpha 0.05 in 2 tails. So there's the 0.05 in 2 tails, because again 1 minus 0.95 would give us 0.05. And so using the row 10 for 10 degrees of freedom and the 0.05 in 2 tails, we would have 2.2281 for our critical value t-score. So that's the idea behind using that table. Alright, so again, there are some requirements for building the confidence interval for the population mean where sigma is not known. The requirements are that the sample is a random sample, the value of the standard deviation sigma is not known, either the population is normally distributed or appears somewhat symmetric with one mode and no outliers, or n is greater than 30. After the requirements are met, a confidence interval can be determined as follows. Use Table 5 to find the critical value TC. Then we can find the margin of error. Looks very similar to what we had last time, except we have S for the sample standard deviation instead of sigma for the population standard deviation. Then once we have our margin of error, we can build the confidence interval by the mean subtracting the margin of error and the mean adding the margin of error. We can round to an extra decimal place to help us with our calculation. Now, again, the student t-distribution is different for different sample sizes. The mean is t equals 0. The standard deviation of the t-distribution varies with sample size but is greater than 1. As n gets larger, the t-distribution gets closer to the standard normal distribution. Now, let's look at some examples. First, we're going to start off with, should we use TC or ZC? In other words, should we use t-scores, Table 5, or z-scores, Table 4? So in this first example, we have n is 9, x bar, the mean of the sample, is 75, s is 15, that's the standard deviation of the sample, and the population has a normal distribution. Well, in that case, since we don't see a sigma mentioned at all, we're going to have to use t-scores. In our second one, we have n is 12, we have x bar is 98.6, and sigma is 0.6. So we do know the population standard deviation, so we use z-scores. In the third one, we have n is 5, x bar is 20, and s is 2. However, the population has a very skewed distribution, which means that we're not supposed to use either one of these approaches to solving the problem because of the skewed distribution. It either has to be a normal distribution or it has to be something that is pretty close, somewhat symmetric, with one mode and no outliers. If you have a very skewed distribution, then you definitely will have things that kind of look like outliers, and it's not very symmetric. Alright, now, how about finding a t-score? So, we have a sample size of 7, simple randomly selected sample from a normally distributed population. Find the critical value, the critical t-score, corresponding to a 95% level. Now here's a big difference between this and what we did last time. 95% would have locked in what the alpha was and where to look in the table. This is only part of the information. We also need the degrees of freedom. In other words, we're going to be looking at a certain column. That's what the 95% will show us. But the 6, that's the row we're going to look at. A different n would give us a different row to look at. So, for degrees of freedom of 6 and an alpha of 0.05, which is in 2 tails. So, here's our 6. Here's our 0.05 and 2 tails. And here we have 2.4469, which, if you rounded it to just 3 decimal places, would have been 2.447. And again, from Table 5. So that's an example of how to find it. Now please note, let's say that the n had been 14 instead of 7. Well, then we would have looked at row 13, 14 minus 1. And even though it's the same column, now our t-score would have been 2.160 instead of the 2.447. So, something very different from using Table 4 and the standard normal distribution. It will vary with the sample size. It'll vary with what row you are looking at. Alright, now we're going to look at constructing some intervals. So, 49 subjects were treated with doses of raw garlic. The changes in their levels of LDL cholesterol have a mean of 0.4 and a standard deviation of 21. Construct a 95% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. Alright, well, we have 49 for our n, so that means the degrees of freedom is 1 less, which is 48. Our alpha is 0.05 because of the 95%, and that's in both tails. If we then look, and again, we're going to look. Now, we don't actually have a 49 row, but we can use 50. Okay, and 50 for the middle column, that's the 0.05. That gives us 2.0086, which to 3 decimal places is 2.009. Again, 50 was the closest row to the 48. So now we can go find our margin of error. The 2.009, the 21, that's the sample standard deviation over the square root of 49. We get 6.027, which 6.0 is probably good enough. So we're going to have 0.4 subtract 6.0, 0.4 plus 6.0. And so it goes from negative 5.6 up to positive 6.4. As a note, since the range includes a mean of 0, a mean of 0 means that basically there was no change, no benefit to the garlic treatment. The garlic treatment might have had no effect. This kind of interpretation will become common if you tend to go from a negative to a positive value. That since then it contains 0, that's telling you that there might not have been any difference in whatever it was you were testing. Alright, next example. Random sample of the births of 186 babies has a mean of 3103 grams and a standard deviation of 696 grams. What is the best point estimate of the mean weight? Construct a 95% confidence level. N is 186. Degrees of freedom is 185. We're going to use the row 200 because that's the closest. Again, 95% gives us an alpha 0.05. So let's look at our table real quick. And again, it goes from 100 to 200. We go across, and there's the 1.9719 or 1.972 for our critical value t-score. 696. Okay, that was the standard deviation of the sample. 186 was the sample size. Don't forget the square root. We come out with 100.6, which we rounded to 101. So 3103 subtract the 101, 3103 plus the 101, and we have our interval of likely values for the mean of the population. So we have taken a sample of 186 babies and created from it an interval that should contain the actual mean of the population. Now, it turns out that if we are given the confidence interval, we can work backwards to find out what the margin of error and the sample mean are. And here's how it works. If we want to find out the sample mean, x bar, basically we're going to add the minimum and maximum values of the confidence interval, the two extremes, add them together, divide by 2. Why is that possible? Well, note that the minimum is x bar minus the margin of error. The maximum is x bar plus the margin of error. When you add those two things together, the margin of errors, the e's, cancel out. I'm left with 2x bar over 2, or just x bar. So if I want to find the mean, I add the 2 and divide by 2. So in this particular case, when my interval went from 6.17 up to 8.53, add the 2, divide by 2, in other words, halfway. And there's my mean, 7.35. If I want to find the margin of error, I simply take the maximum and subtract the minimum and then divide by 2. And so note in this case, when I have the maximum, x bar plus e, subtract x bar minus e, it's the x bars that get canceled out, and I end up with 2e, 2 margin of errors over 2, which is just e. And therefore, to find my margin of error, 8.53, subtract the 6.17, divide by 2, and there's my margin of error of 1.18. Let us go ahead and just go right to a second example. Our confidence interval went from 16.2 up to 29.8. If we take the average of those two numbers, we have the mean of the sample. If we take the difference of those two numbers, and we're always going to take the bigger one, subtract the smaller one. If we take the difference of the two values, the two extremes, then divide by 2, we have our margin of error. And of course, going back to our definition for our interval, if we take x bar, subtract the margin of error, that's how we got the first number, and then x bar plus the margin of error, and that's how we got the second number. And so now we have how to find the confidence interval for the mean when sigma is not known.